Having looked at what the equation of a line in R2 or in two-dimensional space look like, let's see if we can do something similar to describe the equations of a plane in R3 in 3 dimensions. Okay, so again, of course, if I'm trying to draw something in 3 dimensions, it's going to be a little bit more complicated, so I'm going to rely on your imagination or your mental visualization to see what we're doing here. So let's assume that we are in 3-dimensional space, x, y, z, and that the yellow parallelogram there signifies some kind of a plane, which is straight, flat, thin object that runs through space. Okay. Now, you may or may not know what the basic forms of the equation of a plane are, coming from your high school knowledge. But basically, the equation of a plane is just a generalization of the equation of a line, and it turns out that the general equation of a plane is written as ax plus by plus cz equal d. Again, it's a straight object, it's a linear object, so it's not surprising that it is described by a linear equation. In fact, if you go through the notes or the textbook, you'll have a more complete discussion about why an equation like that is in fact the equation of a plane. But for now, let's just remember this is just a generalization of the equation of a line. Now, if we have a specific point in mind, we can actually rearrange that equation and write it like this, which again looks very much like the point slope equation of a line, except that again in 3 dimensions now we would have more than one slope, so we're not really going to call it that way. But the important thing is that we are going to identify, highlight a special point x0, y0, z0 in the plane, and we're going to put everything on the left hand side, leaving just a 0 on the right hand side. So these are 2 basic forms of the equation of a plane. Well, once again, in linear algebra, by using linear algebra, we're going to see a few more of these forms, which are going to be very, very similar to the ones that we've seen for lines. So let's see what the normal equation looks like for a plane. Okay, well, let's have a look at the plane, and notice that a plane, once you identify a plane, there is only one direction which is normal to it. Normal meaning, of course, perpendicular to it. Okay? We can go in that orientation or the opposite orientation, but there's only one direction which is going to be perpendicular to the plane. All right, so if I pick a point on this plane, and I identify another generic point, so x0, y0, z0 is sort of the starting point. If I pick any other point on this plane and I look at the vector once again that joins these 2 points, you'll notice that this vector has to be perpendicular to the normal vector. By definition, the normal vector, again, intuitively you can see that it's perpendicular to everything in the plane, therefore it's going to be perpendicular to that particular vector, which means that the dot product is going to be equal to 0. Now again, I can play the same trick as before. I can use the distributivity of the dot product to rewrite that equation as x, y, z dot and 1 and 2 and 3 equal to x0, y0, z0, 0 dotted with n1 and 2 and 3. And this has exactly the same interpretation as before. Notice that just for the normal equation of a line, in this equation we see the generic point on the plane x, y, z. We see the normal n1 and 2 and 3. Once again, n1 and 2 and 3. This normal vector, we have many choices, but they all have the same direction, so there are multiples of each other. And then we have a special point x0, y0, z0 that we need to identify in order to ground the plane somewhere. And again, as we have done for lines in R2, we can collapse this whole equation in this simpler form, which uses vector notation. And notice this is exactly the same notation as for the equation of a line in 2 dimensions. So the normal equation of a line in 2 dimensions and a plane in 3 dimensions turns out to be exactly the same. If you're smelling some sort of generalization idea, you're right, because in the next class we will see how this can be generalized to even higher dimensional Euclidean spaces. So this, again, we're going to call it the normal equation of the plane, and just like we've done before.